Hello students, welcome you all. In pericyclic reactions, today we will see the analysis of 2+2 cycloaddition reactions by correlation diagram method. In my previous lectures, I explained about the electrocyclic reactions and its analysis by different methods. For example, this correlation diagram method, PMO method, FMO method, and Woodward-Hoffman rule method. So before starting this 2+2 cycloaddition reactions, let's see the brief about this cycloaddition reactions. So cycloaddition reactions where two reacting partner react to give the product. So suppose if simplest cycloaddition reaction, that is the 2+2 cycloaddition reaction. So this is two ethene system. These are the two reacting pi systems. The reacting pi systems here, it may be same reacting pi systems or different reacting pi systems. So this in presence of either heat or light. So cyclic shift of electron will take place, means this pi bond being the loosely held, so they will form a cyclic transition state, involved in the cyclic transition state, and it will give the cyclobutane. So here if you will see in reactant, two pi systems are there, and in product we have the 0 pi bond. Two pi bonds are there in reactant, 2 pi bond, and in product if you will see then it has 0 pi bond. And plus if you will see two new sigma bond is formed over here. So we can say two new sigma bond is formed plus one ring is formed. Okay, in the same way, if you will see the another cycloaddition reaction, for example, when 2 pi system, then 4 pi system, it reacts with a 2 pi system. Here 2 pi system reacts with a 2 pi system. Here 4 pi system reacts with a 2 pi system in presence of either heat or light. It forms a cyclohexene. Cyclohexene is formed, and if you will see that it, as I told, the pericyclic reactions takes place with the cyclic shift of electron and transition state is formed. So if you will see the transition state, then what we will see here, this is one of the new sigma bond is formed, this is another sigma bond is formed, and here new pi bond is formed. This pi bond is this pi bond, this is new pi bond is formed, and this pi bond is broken down, this pi bond is broken down, and this pi bond is also broken down. Okay, so formation, in transition state we know the formation, breaking and formation of bonds takes place. So this is the transition state which is formed over here. And if you will see here, then total number of pi bonds in reactant 3 pi bond, and in product we have 1 pi bond, plus 2 new sigma bond is formed, and plus 1 ring is formed over here. Okay, so in general way, what you can see, in general way, if you will see in cycloaddition reaction, in product if we have n pi bond, in reactant if we have n pi bond, then in product we have n minus 2 pi bond, plus 2 new sigma bond would be formed, and plus 1 new ring that would be formed. So this is the overall conclusion if you will see in a cycloaddition reaction there. In the same way, if suppose if we have this is our cyclopentadiene, and this cyclopentadiene in presence of malic anhydride. This is malic anhydride. So this in presence of either heat and light. So this will also undergo cycloaddition reaction. So this is our 4 pi system, and this is 2 pi system. This can be regarded as a 2 pi system. So again the cyclic shift of electron will take place. This will go over here, this will go over here, and this will like this. So one of the this is sigma bond that would be formed in between this carbon and this carbon. Another sigma bond that would be formed in between this carbon and this carbon, like this. So what would be the final product? The final product, if you will write, okay, so this is this is our bridged carbon, and this bridged carbon is shown in this way, and this new pi bond is formed over here, and so this would be the product. So this is an example of these two. When diene, it reacts with the dienophile. Here also diene, and this acts as a dienophile. So this is an example of a Diels-Alder reaction, and we may also see this is a intermolecular Diels-Alder reaction. Intramolecular Diels-Alder reaction. So if you take the example, then diene and dienophile, they are present in a same molecule. So if we see, then this is our diene, and one of the dienophile, this is here. So diene and dienophile, they are present in the same molecule. So this also, it gives the pericyclic reaction in presence of heat or light. So cyclic shift of electrons will start, and here this will go over here and like this. So what we will get finally, so one of the new pi bond that would be formed over here, and so one of the new sigma bond is formed between this carbon and this carbon, and another sigma bond that would be formed between this one and this one. So one of the sigma bond is formed between this one and this one. Another sigma bond is formed between this carbon and this carbon. Okay. So this would be the product in this case. Or otherwise we may write this product. Suppose I give the number to it 1, 2, 3, 4, 5, 6, 7, 8, 9. In the same way, 1, 2, 3, 4. This would be 5, 6, 7, 8, 9. So I may write this product. Okay. So this is our 1, this would be 2, this is carbon 3, this would be carbon 4, this is our carbon 9, and this is carbon 8. Okay, one of the bridge, 2 carbon bridge is present in between first and fourth. So 2 carbon bridge is present in between first and fourth, whereas if you see, then there is a this carbon is present between 6 and 8. Okay, so this is our 6th one, and this would be 5th carbon, because from first carbon 6th carbon is attached, from 4th carbon 5th carbon is attached, and 6th and 5th. So between this 6th and 8th carbon, one of the carbon is 7th one. So I may write in this way. Okay, so this is an example of, this is intramolecular Diels-Alder reaction. And this would be, these two are the intermolecular Diels-Alder reaction. Okay, so this is about the different types of the cycloaddition reaction. So this is 4n electron system, and these are the example of 4n plus 2 electron system, where 6 electrons are involved in this cycloaddition reaction. Okay, so now before coming to the analysis of this cycloaddition reaction, or analysis of 2 plus 2 cycloaddition reaction, we should know the two terms which would be used in this cycloaddition reaction. In electrocyclic reactions, the two terms that we were using, that were the conrotation and disrotation. Here in cycloaddition reaction, we will use two terms. One is called as the suprafacial and another is called as the intrafacial. Suprafacial and another term is the intrafacial. So what are this suprafacial? What about this suprafacial and intrafacial? So suppose if the two orbitals react from the same side, then that is called as the suprafacial, and if two orbitals react from the different side, then that is called as the intrafacial. So suppose if we have if these two orbitals react, same side orbitals react. So if supra means same side orbitals react, or same side orbitals interact during the bond formation, and that is called as supra, and intra means when opposite side orbitals interact, then that is called as the intrafacial. So here if you will see, then this is suppose 4-pi system. These are the orbitals of this suppose butadiene. Then here if these two, because the only end orbitals are involved in the bond formation, that's why we are only concerned here with the end orbital. So here this two same side if orbitals are involved in the bond formation, then this is called as the 4s, that is supra. S stands for the supra. And suppose if we have this ethene, when butadiene interact with the ethene system, and in ethene also if same side orbital is interacting, here also the same side orbital is interacting, then this is the 2s system. So 4s system and 2s system interact to give the cyclobutene. So it gives the cyclobutene. So this is an example of 4s plus 2s system. This would be an example of 4s plus 2s system. In the same way, suppose if we have this butadiene, suppose in butadiene we have the opposite side orbitals interact, opposite sides of this end orbital, opposite side end orbital interact, then this is our 4a system. These are the opposite side orbitals, and here suppose same side orbitals is interacting, then this is our 2s system. So it interacts in this way and this interact in this way. So what type of system it would be? It would be 4a plus 2s system. Okay. In the same way, I may draw so this would be an example of, this is same side orbitals are interacting. Okay, so this would be 4s system. Here opposite side orbitals are going to interact. This is a 2a system. So what type of system it would be? It would be 4s plus 2a system. In the same way, suppose I take this one. Now this one is an example of opposite side orbitals are interacting. That's why this would be 4a. Here also suppose I write this opposite sides orbitals are going to interact, then this will be 2a. So overall what I can write, it is an example of 4a plus 2A system. So cycloaddition reaction will take place between these two pi systems. So this is about the suprafacial and intrafacial, and we will use these terms during our cycloaddition reactions. Now let's analyze this 2 plus 2 cycloaddition reaction. So now you will see about 2 plus 2 cycloaddition reaction, or analysis of 2 plus 2 cycloaddition reaction by correlation diagram. So we will see its correlation diagram. So how can we understand this? Let's see it. So if you will see, then this is our simplest 2 plus 2 cycloaddition reaction. Okay. This is simplest 2 plus 2 cycloaddition reaction. Now in this case, if we remember the cycloaddition reaction for the electrocyclic reaction, then in cycloaddition reaction, first of all, before drawing this correlation diagram, we take the molecular orbitals which are involved in this reaction. So if you will see, then molecular orbitals involved in this reaction, that would be, this is one pi system, this is another pi system. So corresponding to this pi system, the molecular orbitals, that would be pi 1 and pi 1 star. Suppose this is pi 1 and this is pi 2. So corresponding to this pi 1, the molecular orbitals involved, that would be pi 1 and pi 1 star. Similarly, corresponding to this pi 2, the molecular orbitals involved, that would be pi 2 and pi 2 star. Okay. Now if you will see here, the new sigma bond, this is formed over here. This is one sigma bond, this is the new sigma bond which is formed over here. Suppose this is first sigma bond, this is the second sigma bond. Okay. And so corresponding to this sigma bond, the molecular orbitals involved, that would be sigma 1 star, and sigma 2 and sigma 2 star. Now in correlation diagram, what we see, what we do in correlation diagram, the orbitals of same symmetry, are correlated in reactant and product with the help of a straight line. Okay, first of all, we will see the molecular orbitals, means molecular orbitals of same symmetries in reactant and products are correlated. Suppose if this has S symmetry and this has S symmetry, then that can be correlated. If suppose this is asymmetry and this is asymmetry, then these two can be correlated. So that's why we should see the symmetries of orbital in reactant as well as product. Suppose if we see the asymmetry, suppose if we see a C2, so for example in electrocyclic reaction, what we saw, if reactant orbitals are C2, have a C2 symmetry, then product orbital should also have the C2 symmetry. In the same way, if reactant orbital having the sigma or mirror plane symmetry, then product orbital will also have the mirror plane symmetry. So same symmetry orbitals are correlated in reactant and product. Similarly, here also we will see the symmetries. So whether what type of symmetry we can see over here. So here, if you will see, these two pi systems are present over here. Here this cyclobutane is formed. So we will not see any C symmetry. There is no C1 C2 symmetry. No rotation of axis is present over here as a symmetry. So only symmetry which is present over here is the mirror plane symmetry. So suppose if you would draw one of the mirror plane like this, then if you will see, then this divides it into the two equal half. So this mirror plane that I may write it as a sigma V. This is the vertical mirror plane. In the same way, if I draw one of the mirror plane over here, then this also divides this cyclobutane into two equal half. So this will have a horizontal, this can be written as a horizontal mirror plane sigma H. So as you can see, in product we have sigma v, vertical mirror plane, as well as the horizontal mirror plane. So in reactant also in pericyclic reaction, reactant should also have the sigma h as well as the sigma v. So if I draw here, then no doubt this is having the sigma v, and it is also having the sigma h. Okay, so sigma v and sigma h both are present in reactant as well as product. Now if you will see, then so what different types, how the orbitals can interact, if you will see, then this is our pi 1, suppose pi 1 of this one, suppose, and suppose this is pi 2. One is pi 1 and there is pi 2. So one of the type interaction is this one. So this is the pi 1 plus pi 2. This is pi 1 plus pi 2. Okay, this is one of the interaction. Another way of interaction, this would be the another way of interaction. Pi 1, suppose this is our pi 1, this is pi 2. So if this is pi 1, then, and if pi 1 minus pi 2, if I want to write pi 1 minus pi 2, and this is pi 1, and minus pi 2 means this would be minus, this would be minus, and this would be plus, this would be plus. So this is pi 1 minus pi 2. Another way of interaction, now next way, that is pi 1 star plus pi 2 star. So pi 1 star, how can we write this pi 1 star? Plus and minus. This would be the pi 1 star, and these lobe will have minus sign, this will have plus sign. Now this is pi 1 star, and if this is pi 2 star, then, and plus sign is present over here, then pi 2 star plus minus. This is the pi 2 star, and it is adding in this way. So that's why I have same sign, plus minus plus minus. So this is pi 1 star, this is pi 2 star. Another way of interaction of this orbital 2 pi system can interact. So suppose pi 1 star minus pi 2 star. This is pi 1 star minus pi 2 star. So if we see the pi 1 star plus minus, this would be pi 1 star. And what about this pi 2 star? Minus, because this minus sign is present here. In place of this plus, we have minus. That's why the sign will get interchange. So if it would be minus, this would be plus, and this would be plus, this would be minus. So in this way, this can interact. Okay. Now if these interact to give a sigma bond that would be formed, new sigma bond that would be formed. So after interaction, a new sigma bond that would be formed, and the new sigma bond that can be shown in this way. So a sigma bond is formed between these two. So this is plus, 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 and these are having the minus sign. So this is interaction. This interaction is the sigma 1 plus sigma 2. Okay. Now when they will interact, then what we will get? We will get so plus minus. So if they interact in this way, what name I can give it? So this is, because this is plus plus means sigma bond is formed, plus 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 plus. So this is sigma 1. If this is sigma 1, that would be sigma 2. So plus sigma 1 plus sigma 2. And what about this? This is sigma 1 star, and this would be sigma 2 star. This would be sigma 1 star, and this would be sigma 2 star. So we can write it sigma 1 minus sigma 2. So sorry, this, yes. So this is sigma 1 star and plus sigma 2 star. Sorry. So this is sigma 1 star plus sigma 2 star. Now when they interact to give the final orbitals that would be formed. The final orbitals would be something. The sigma bond would be formed between these, this one and this one. Sigma bond would be formed. So it is minus, plus, plus, minus, and same here, plus, minus, and minus. So this would be, I think, they should be plus. Okay. So yes. So this would be plus. Okay. So what name I can give it? So this is sigma 1, and this is also same side in interaction, means this would be sigma, not sigma star. So but minus sign is present over here, that's why it is called as a sigma 1 minus sigma 2. Now when they will interact, then what name I can give it? So these are also interacting, so it will have minus sign, plus, minus, minus, plus, plus, minus. So what you will see? So what type of bonding over here? This is sigma star. This is sigma 1 star. And what about this? This is also sigma 1 star, but sign is opposite to it. Here plus minus, this is minus plus. That's why sigma 1 minus sigma star. So this is our sigma 1 plus sigma star. This is our sigma 1 minus sigma star. Just sign is reversed. Sign is reversed. That's why minus sign is coming over here. Now if you see the symmetries. So we are concerned with the sigma V symmetry and sigma H symmetry. So if you will see the symmetries over here, then let's see the symmetry. One we are concerned with the sigma V symmetry, and another we are concerned with sigma H symmetry. Now what about here, what type of symmetry is presented here? If you see the particular plane, whether this is symmetric with respect to sigma V, in front of plus we have plus, in front of plus plus, minus minus, so it is symmetric with respect to sigma. Now if I draw the horizontal mirror plane, whether this is symmetric with respect to horizontal mirror plane, so this is our sigma H. This is our sigma V. So yes, in front of plus we have plus, in front of minus we have minus, in front of plus we have plus, in front of minus we have minus. That's why it is symmetric with respect to sigma H. In the same way, I should draw the mirror plane, horizontal mirror plane and vertical mirror plane here. So again, if you will see about this vertical mirror plane, plus plus, minus minus, that's what is symmetric. Now horizontal mirror plane, plus minus, that's why it is anti-symmetric. Now what about this? Draw horizontal mirror plane. In front of plus we have minus, that's why it is anti-symmetric. And what about here? In front of plus plus, in front of minus minus, so this is symmetric. Now what about in this case? Vertical mirror plane, in front of plus we have minus, so that's why it is anti-symmetric. Horizontal mirror plane, in front of plus minus, minus plus, that is again anti-symmetric. Okay. Now suppose if you see this sigma V and sigma H in product orbital, molecular orbital. So again in product we should also see, draw the vertical mirror plane, in front of plus plus, that is symmetric. Now draw one of the horizontal mirror plane, in front of plus 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 plus, that's why again symmetric. Now what about this? Here if you will see, then in front of plus we have plus, in front, now this one, in front of plus we have minus, in front of plus we have minus, so mirror, there is no mirror plane, so anti-symmetric. Now if you will see here, in front of plus we have minus, anti-symmetric, horizontal mirror plane, plus plus, minus minus, symmetric. Now in this case, plus minus, that's why anti-symmetric. Now draw horizontal mirror plane, plus minus, it is anti-symmetric. Okay, so this is like this we can see. So SS SAASA. Okay, so these are the now we have to join the orbitals of the same symmetry. So in correlation diagram, the correlation diagram, first of all, let's see, these are the reactants and they react either in thermal condition or in photochemical condition to give us cycloprotein. Now if I draw the reactant molecular orbitals, 4 molecular orbitals are present in a reactant and 4 molecular orbitals are present in a product. Now, so this would be pi 1 plus pi 2. Now this would be pi 1 minus pi 2. Here it would be pi 1 star plus pi 2 star, and this would be pi 1 star minus pi 2 star. In the same way, this is sigma 1 plus sigma 2, sigma 1 minus sigma 2, sigma 1 star plus sigma 2 star, and this would be sigma 1 star minus sigma 2 star. Now what we saw, so if you see what type of this was our pi 1 plus pi 2. Okay, this was pi 1 minus pi 2. Now this is plus, plus minus and plus minus. So this is pi 1 star plus pi 2 star, and this is pi 1 star and minus pi 2 star. This would be minus, this would be plus. Okay, I have only drawn these interacting sign for the interacting molecular orbital. You may draw for this one or these lobes also. Okay, so now, so pi 1 plus pi 2, it is the lowest. I have drawn at the lowest energy because two interacting orbitals both have the this plus plus sign. Two bonding interaction are present over here. If we compare this pi 1 plus pi 2 and pi 1 minus pi 2, then two bonding interactions plus 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 plus, whereas here there is two anti-bonding interaction. That's why no doubt this pi 1 plus pi 2, that should be at lower energy in comparison to the pi 1 minus pi 2. Now what about this two, pi 1 star plus pi 2 star and pi 1 star minus pi 2 star? So here again if you see, two bonding interactions are there in pi 1 star plus pi 2 star plus plus minus minus, but here in pi 1 star minus pi 2 star there is one anti-bonding interaction, another anti-bonding interaction. That's why this will go to the higher energy. Now in the same way we can decide for the energy of these molecular orbitals. Now suppose I draw for sigma 1 plus sigma 2. What was sigma 1 plus sigma 2? So I should draw like this. This is our sigma 1 plus sigma 2. Okay, and no doubt this sigma 1 plus sigma 2, that would be at lower energy in comparison to pi 1 plus pi 2, because sigma bonds are the stronger bond and more stable bond in comparison to the pi bond. Now sigma 1 minus sigma 2, this was sigma 1 minus sigma 2 plus plus minus minus. This is sigma 1 minus sigma 2. What about this sigma 1 star and plus sigma 2 star? this is sigma 1 star plus minus, this is sigma 1 star, and plus sigma 2 star, this is plus sigma 2 star. Now this one, now this is sigma 1 star, plus minus interaction is sigma 1 star, and here minus plus. So I should reverse the sign of this. So this is our sigma 1 star minus sigma 2 star. Now if you compare the energy between pi 1 star and sigma 1 star plus sigma 2 star, then pi 1 star has two bonding interaction, whereas the sigma 1 star and sigma 2 star has two anti-bonding interaction. That's why it will be at higher energy, this would be at lower energy. Now if you will compare these two, then this is having the plus minus two anti-bonding interaction, here also two anti-bonding interaction, but sigma bond, that would be at higher energy and this would be at lower energy. Okay. Now, so that's why the energy levels that I have drawn should be in a similar manner. We should draw the energy levels for these two. Now, so this about this symmetries. So this was having SS symmetry. Okay, this was having SAA symmetry. In the same way, this was having this AA symmetry, and this is also having SS symmetry. Now, what about this? First of all, you should see for the sigma vertical mirror plane, then horizontal mirror plane. About vertical mirror plane, this is symmetric with respect to vertical, and it is anti-symmetric with respect to the horizontal mirror plane. What about this? You will see it, and this is anti-symmetric with respect to the vertical mirror plane. And what about this? This is horizontal mirror plane. This is symmetric with respect to the horizontal mirror plane. In the same way, we can decide for this. No doubt, this is SS, this is AA, and if you see here, then draw one vertical mirror plane. So it is your, if you see the mirror, then it is anti-symmetric with respect to this one, and this is symmetric with respect to the horizontal mirror plane, and this one, this is symmetric with respect to the vertical mirror plane. What about this one? This is anti-symmetric with respect to this one. Okay, so now we can easily, so I have written the horizontal symmetries as well as the vertical. First of all, I should write the vertical symmetry, then horizontal symmetry. In the same way here also, first I should write the vertical symmetry, then horizontal symmetry. Now we can do the opposite, we can write in opposite manner also, but in both the case, if I write horizontal plus horizontal first and vertical second, then here also I should write the horizontal first, then vertical second. Now you can easily draw the correlation line. You can easily correlate it. Now this SS can only be correlated with SS because they both have the same symmetry. Now SA can only be correlated with SA. It can't be correlated with AS. So I should correlate here. This AS can only be correlated here, and this can only be correlated over here. So like this. Okay. So now whether this is whether it is thermally allowed or photochemically allowed, in what condition it is thermally allowed, in what condition it is photochemically allowed. So let's see. So now, so in this reaction, 2 plus 2 cycloaddition reaction, 4 electrons are involved in the reaction. 2 pi electron here, 2 pi electron here. In the same way, 2 sigma electron here, 2 sigma electron here. So 4 pi electrons are involved here. So under thermal condition, what we can write? Under thermal condition, what you can see? 2 electrons would be present over here and 2 electrons would be present over here, means in a ground state. Electrons are present in a ground state only. So what I can write, or otherwise I should, for simplicity, we can name it as a, suppose this is psi 1, this is psi 2, this is psi 3, and this is our psi 4 molecular orbital. This is psi 4. In the same way, we can name it as a, suppose this is A, B, and this is C, this is D. Okay, for simplicity I have given the different name. In place of sigma 1 plus sigma 2, we can write the A like B, C, D. Now, under thermal condition, if 2 electrons are present in psi 1 and 2 electrons are present in psi 2. Okay, so these 2 electrons, psi 1 electrons are going into A, whereas the psi 2 electrons are going into the C. So this is when electron is going into C, it is going into the first excited state. So this is first excited state, whereas this is our ground state. This is ground state. So this is not energetically favorable when from ground state electrons are going into this first excited state. So this is not energetically favorable. Now under photochemical condition, under thermal condition and under photochemical condition, so one of the electron will excite to this psi 3. One electron will get excited to psi 3, and now what you can write, psi 1 having the 2 electron, psi 2 having the 1 electron, psi 3 having the 1 electron. Now, so this psi 1 electron going into A, 2 psi 1 electron going into A, psi 2 electron going into C, 1 psi 2 electron is going into C, and 1 psi 3 electron is going into B. So if you will see, then this is our first excited state, and this is also first excited state. This is also first excited state. So the electron movement from first excited state to first excited state, this is energetically favorable. So that's why photochemically this is allowed. Okay, so finally what you can write? Finally I can write for cycloaddition reaction, I have drawn for this the 4n electron system. For 4n electron system is thermally, 4n electron system, thermally it is disallowed, and photochemically it is allowed. So in my next lecture you will see that for 4n plus 2 electron system, the 4n 2 electron system, photochemically it would be disallowed and thermally it would be allowed. That we are going to analyze in my next lecture. So for when I will take the example of 4n plus 2 electron system. So this is about the analysis of 2 plus 2 cycloaddition reaction by this correlation diagram method, and in next lecture you will see the correlation diagram for 4n plus 2 electron system. Okay, thank you.